We should start to continue our session. And the next speaker is Gaiane Panina, but it is the talk by two authors, Mamaev and Gaiane Panina, and presented by Gaiane.
Thank you very much. And to tell the truth, the most of the job which I am going to tell about was done by my diploma student, Mamaev. And so let me start with the formulation of the problem. So assume that we have a smooth manifold Mn. This is a smooth manifold. And a function, a real valued function f, which takes Mn to real numbers. And now I will spend 2 minutes or maybe 3 minutes in a brief introduction to Morse theory. So this picture can be visualized, and it is usually visualized, for instance, in Milner's book like this. Let us assume that f equals the z coordinate, and the manifold is somehow embedded in, so this is the manifold Mn. It is somehow embedded in a big Euclidean space, and the function f just is one of the coordinates. And then it makes sense to look at the gradient of f. Usually it is taken with the sign minus. This means that at each point of the manifold M, and of course we assume that there is a Riemannian metric, but let us just keep it. We have a gradient, anti-gradient vector, which is tangent to the manifold. And generically, there are there is only finite number of points where this gradient vector vanishes. So for this particular picture, when the manifold is the sphere with two handles and the function is the z coordinate, gradient vanishes here, 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 and here only. And in all other points we have a non-zero gradient, and if we take the enveloping trajectories, we see that we have lines, and which are called gradient lines, and the entire manifold M is stratified by these gradient lines. And the story is the following: that each gradient line, it starts at some of the critical point and ends at some other critical point. So it all looks like this. For instance, for instance, this line goes from here, from the top to the bottom, and so on. And so these are critical points. Critical points. These red points are critical ones. And Morse lemma says that if you take a neighborhood of a critical point, and if the neighborhood is sufficiently small, then the function f in this small neighborhood looks standardly. So in a neighborhood of each critical point, we have some standard representation of the function f. For instance, if n equals 2, so in this picture n equals 2, here at this point, f looks like this. In appropriate coordinates x and y, it is c, which is this some constant c minus x squared minus y squared. Why so? Because this is a maximum. And then we say that the Morse index equals 2. Why 2? Because here we have two negative squares. Okay, here at this point, we have somewhat converse. F of xy of equals some other constant c prime plus x squared plus y squared. And here we say that the Morse index is 0. And there are also 4 saddle points. And for saddle points, we have let's write this way, minus x squared plus y squared. And then we say that the Morse index is 1. Generically, in the general situation, in arbitrary dimension, nothing interesting adds here. So generically, we have that in a small neighborhood of a critical point, with an appropriate system of coordinates, the function f can be expressed as xn. So there are many variables here. Again, some constant c, and then minus x1 squared minus so on minus x mu squared plus x mu plus 1 squared plus so on plus x n squared. So the same. The only difference which occurs here is the number of negative signs here. And this is an invariant. This does not depend on the choice of the coordinate system. And this mu is called the Morse number, Morse index. Morse index. This is definition. Okay, I think that's all about Morse theorem so far, Morse theory so far. And so, so we always have, whenever we have a maximum, global or local maximum, we have that the Morse index at a global of a maximum is always n, always the same as the dimension of the manifold. Whenever we have a minimum, global or local one, the Morse index is always 0 because there are no negative terms here. And in between, we have a variety of possibilities. So the Morse index, it is always greater or equal than 0 and smaller or equal than n. This is minimum, and this corresponds to maximum. Okay, and now the question. So it is an interesting story because the question that this problem came to my mind first, and I didn't expect the answer we received, and so it sounds somehow counterintuitively. So the question is the following. Okay, let us forget about very complicated manifolds. Let us think that we have just a ball, BD. So please imagine this ball as the ball centered at the origin in the d-dimensional Euclidean space. And assume that we have a function f, which takes the ball to real numbers. Okay. We assume that f is a Morse function, which means that there are a finite number of critical points, and all critical points are Morse points. This means that they all have Morse indices. So this quadratic form does not degenerate. Moreover, I assume that the unique critical point of the function is at the origin with a unique critical point at 0. So this is the ball BD, and this is the origin, which is the center. Okay. Assume that we know the restriction of the function f to the deleted ball. So we take the big ball and we delete a neighborhood of the 0. So it is BD minus, let us write it this way, epsilon times BD. So I take the big ball and I cut out a small ball centered at 0. So you do not see the critical point itself, but you know all the rest, the behavior of your function in the complement of the neighborhood of the 0. Okay, so you know this question. Can the Morse index be recovered by this data? So once again, we have a function in a ball with a unique critical point. We know in advance that the critical point is just 1, and it is non-degenerate. So there is some Morse index. Okay, and the question is, can we recover this index without looking at the point and without looking at its small neighborhood? So let me tell some first elementary observations. So the first, what I want to say is that sometimes the question is yes. Sometimes yes. Just imagine that we have the following. So let BD be B2. So we have two-dimensional ball, just a circle, and we cut out this small ball, and we have a function f. And when you look at the gradient lines, so these are gradients, they all look like this. So gradients all point here. So can you tell me anything about this critical point? What is it, maximum or minimum or a saddle point? If the function grows in this direction, then more or less obvious that we can expect nothing by maximum here. Then we have maximum here, and therefore the Morse index, so Morse index of a maximum is 2. Why? Because assume it is a saddle point or a minimum point. Then there are outcoming gradient lines. So this is anti-gradient lines, and gradient lines, they point upwards. So if it is not a maximum, then there should be an outgoing gradient line, which I wanted to draw by red. Do we have colored chalk? I found only one, very small. Okay, then there would be.
What is Morse function? Because I don't know.
Okay, Morse function is a good function, which has a finite number of critical points, firstly, and secondly, this second differential does not degenerate at the critical points. So the Morse indices are well defined. Well, because to tell the truth, could happen that some of these terms vanishes and instead there stands 0. This is what we do not like. So we do not like degenerate second differential, and so let's write minus x1 squared. Okay, just a good function. So if it were not a maximum, then there would be an outgoing gradient line. Okay, and so it goes out, and it cannot terminate just terminate, because gradient lines, they go from critical points to critical points, or from critical points to the boundary. So it cannot just stop somewhere here. It should go somewhere out of this small ball and then turn to the boundary. And by condition, this does not happen. Okay. So sometimes the answer is positive. What else can we say? Okay, the second item is a little bit more complicated, but still it is easy. So we have this is BD. This is the domain where we know our function. And here is our unknown critical point. Let us take a sphere which sits in between. So this is the sphere of dimension d minus 1. And at each point of the sphere, we have a gradient of f, which is never 0, because we agreed that the gradient never vanishes except for the center. Because just remind that the points where the gradient vanishes, these are critical points by definition. And there are no other critical points except for the center. So at each point, we have a well-defined non-zero vector field. Therefore, we have a mapping from SD minus 1 to SD minus 1, where a point x is mapped to gradient of f of x divided by the module. This means that for each point we take to the sphere SD, which has the same, which corresponds to this direction. So we have a map from a sphere to sphere, and therefore we can speak about the degree of this map. And degree, let's call it, I don't know, let's call it phi sub f. The degree of phi sub f, well, it knows, let me say so, it knows the parity of the Morse index. Therefore, looking at the behavior of the gradient vector field on the sphere, we can decide, is the Morse index even or not? So we can read off the parity of the Morse index. And for instance, if it cannot be, so we cannot confuse a minimum with a saddle point because the parities are different. But the question remains, whenever we live in the plane, just in the plane, can we tell a maximum from a minimum or not? Parity doesn't help because for maximum and minimum, the Morse indices are 0 and 2, one and the same parity. And so the answer is, let me tell, conjecture. Conjecture is the following, that we cannot distinguish between Morse indices of the same parity, mu and mu plus 2 times k, whenever they are greater than 0 and smaller than n. Okay, so in particular, so this is a general conjecture. It is proven for k equals 1 for the time being, and the proof is due to Dan Mamaev. Let me give you just how can you visualize this fact. Assume you are doing a hike. So there is a landscape, mountains, valleys, lakes, and also holes. And while you walk, you observe that at some point there is a piece of fog, so you cannot see what happens there. And you are wondering, is there a lake, or instead there is a mountain inside this fog? But you cannot see through the fog. But the piece of fog is quite small, so you can go around, you can investigate the vicinity of this fog place. So so the question is, can you tell without penetrating inside the fog, is there a mountain or a lake? And the answer is, well, sometimes yes, that's possible, but sometimes it is not. Now let me pass to exact formulations. My time is almost over, but still. Okay. So theorem. There exists a function which is defined on BD minus epsilon times BD to R, such that let us formulate it for dimension 2, such that f can be extended to a function from the entire ball with a maximum at the origin. And also the same can be extended to a function with a minimum at the origin and with no other critical points. Okay, so probably I have some time to do the proof for dimension 2, of course, because very little time is left. I just want to say the following, that the first observation in this direction was done by Semyon Podkorytov, because I first addressed him with this problem. And he very soon provided a picture demonstrating that indeed this is true. And what Dan did is that he provided a general approach which works not only for dimension 2, but for any other dimension. And the idea of this approach can be demonstrated. So let me show you how it works. Okay, let us consider a linear function f from R2 to R. Just a linear function such that its gradient lines go this way. This means that the graph of this function is a flat slope like this. Okay? And let us also take a sphere which lives here. Okay. And then we do the following. We replace this sphere by something like this. Something like this. And now I am interested in the critical points of the restriction of f to this sphere. This is S1. It's a circle, S1. Let us call it S1 because I have no time to give more notations. So if we restrict the function f, which is linear, to this circle, there appear critical points of the restriction. So the linear function has no critical points, but the restriction has. So here is the maximum. Here is a local maximum, local minimum, and a local minimum. And the gradient vectors look like this at these points. Now the idea is the following, that we can perturb this big function f, this global function f, by putting here very close to this is a nose, okay? Very close to this nose, we put a point which is a local maximum. This is a local maximum. So I alter the function f, which is defined so far on the plane. And what I do, I also replace this piece of this nose like this. It is a trick used by Sergei Barannikov in his already old papers on Morse-Barannikov complex. And I also want to give credit to Sergei Barannikov because the inspiration, the combinatorial inspiration of what do we have to do to create such an example, the combinatorial inspiration comes from Barannikov complexes. So Barannikov complex does not give an algorithm of creating such examples, but they give somehow a hint. What should one do to arrive at such examples? Okay, we take this way. The second, what we do. And so this trick of pulling the nose over means that we have, again, a critical point. Instead of this, we have a critical point here, and the gradient vector points here. So we have a combinatorial object. It is a circle with some critical points and with the indications of the gradient vectors at them. And now you see, if we take a small neighborhood of this circle, we arrive at a function which is which is defined on a deleted ball and which is extendable to a function with a maximum point inside. So this will be one of the extensions there. So we can just apply a diffeomorphism to this drawing and to make this circle a real circle. And this maximum point goes here, and it is fine. Alternatively, we can do more or less the same, but in the other direction. So I create this way the nose is created this way, and I put a minimum point here, and absolutely similarly to this construction, I can pull this nose this way. And then I create a different function, which is, well, it is a different function, which is extendable to a function with a minimum in the center. Okay, so we have here function f. We have here a function g. They are different, so these are not yet what we want. And now the idea is the following, that this combinatorial picture, let me once again draw this picture. So let it be A. And the vector points here, then there is B. And the vector points outward, then there is C. And the vector goes here, and D goes here. And if you look at this, the analogous picture for the second drawing, you will get the same. So the combinatorially, the pictures are the same. And all together, if you take these two pictures together, you can do the following. What is actually done. So you start with the first circle. This is big first circle. And you take small annulus here, and you take the function, how do we call it? F. So this is the function f. It is here. Now you take this is the second circle, and here we have the function g. And now, so the function f can be extended in such a way that there is maximum in the center. The function g has a minimum in the center. And if we apply a linear extension here, so here we just extend bilinearity, then we obtain the function with nowhere vanishing gradient. This is very important, that we should not create extra critical points. So we fight for the non-vanishing gradient. And the gradient does not vanish because of because of the correspondence of these combinatorial pictures. So this is how combinatorics worked here. And now what we have? Now we have a function here. Its extension with a minimum in the middle. And by construction, we also know that the function f is extendable. So here is the picture with a maximum in the center. And of course, this is not all the story, because if you apply linear approximation, then you lose smoothness here. But it's not the problem. So this is just a technical problem. And what is good about this approach? Because such noses, you can pull these noses in any dimension, so to say. And so you repeat more or less the same. The important part was to understand what does pulling a nose mean in bigger dimensions. But it all is doable in bigger dimensions. And so what we proved that what is proven for any dimension in dimension n. An analog of this theorem for Morse indices mu and mu plus 2. So these two indices in certain cases are indistinguishable, cannot be distinguished. So I mentioned already Dan, who did the most of this work. I mentioned Simeon Podkaritov. We are grateful for him because he was the first to observe this phenomenon. In the very beginning, I thought that Morse index can be recovered completely. And I mentioned Sergei Barannikov, whose beautiful ideas helped us to do this. And thank you also, Koля, for organizing the alive sessions of his conferences. And I stop here. Thank you.
Thank you very much, Gaiane. It's my special pleasure to see usual way of presentation by Blackboard.
And it's so pleasant to be here and remember how should I manipulate with a chalk. I didn't forget it during this year. Thank you. No, it's fine. Your fault.
Preferable way of presentation.
Thank you.
Вопросы? Questions? Comments?
Well, Daniel Mamaev is also in the same group as Victor now. That's his diploma.
He's my diploma student. Yes, Daniel Mamaev one really very good. He's watching to us, so let's not praise him too much.
If no one more questions or comments, we should thank Gaiane again.